Yes, good afternoon, everyone. My name is Carsten Dahl. As you heard, I come from Nov Flexibles, which until a year and a half ago was NKT Flexibles. And I'm going to talk about condition monitoring of flexible risers for operation and maintenance. Before I get into the details, I'd like to just tell you a little bit about Nov Flexibles. It is located in Denmark with our main office in Copenhagen, and we have a factory in Kalundborg at a deep water harbor, 100 kilometers from Copenhagen. And here we have our total production and our storage, large scale turntables and stuff for long length pipes, and we have all our testing for during production in here. At the head office and in Kalundborg together we have more than 300 engineers working on flexible pipes within the development, including our materials development department and stuff, and within engineering design, and within manufacturing, and within servicing after delivery. In addition, we now have a new factory in operation in Açu, outside campus in Brazil. So now that is focused very much on the Brazilian market. Regarding services, we have a number of different services that we provide on a regular basis to the customers, and they can sort of basically be divided into engineering services, offshore services, and condition monitoring. Under the engineering services, we take part or supply concept studies, feeds or pre-feeds, where we look at the viability and best solutions for flexible pipe systems, and look at gaps for different solutions. And then we participate in early stages of projects regarding planning for integrity management during operation. And then we have quite a large activity regarding reassessments, which is related to pipes and service, and where a lot of questions where there are requests regarding changes in operational conditions. It could have been run off piste for a while, a riser or so, and there may be desires for a prolonged lifetime, and those assessments are also performed by us. And we use the basic information and all the stuff we have back from the design phase, so we know in detail what the pipe looks like, and therefore also we can go fairly close in our assessments. When it comes to offshore services, actually the first one illustrated is it's a bit schematic, but there's a lot of requalification. For example, when spare pipes are in storage around the world, we go out and do inspections and testing of them before they are taken into use, brought offshore for installation. Our people from the factory go offshore for integrity testing, typically annulus vacuum and volume testing, and there we send typically one of our test supervisors from the factory together with an engineer or one of our offshore technicians to perform the work. So they do the assessments on the spot and communicate with the designers at head office if there are any things that become unusual, and we can agree on what other aspects to look at in order to identify why we get an anomaly in the results. Then there's the odd offshore repair, which is also done as a service. What I'm going to focus on today is the condition monitoring, and especially the embedded monitoring, which is something that we've worked on for a number of years, and now we are very far in the qualification, and we are well on the way in the supply of instrumented systems using this integrated monitoring. And just before we get to that, I went a bit fast. We have, just to put it into context, we have the DNV model here for integrity management process, and there the gathering of information is an essential part in doing an assessment, and then which leads to mitigation or repairs, and then again leading to reassessments and planning for the next loop. At present, it has been mentioned by some of the previous speakers. I didn't know what everybody was going to say, so here's a bit of repetition. There's some basic methods used by everyone, I think, which is visual inspection of the pipes or the pipe systems, annulus vacuum and volume testing, vent gas monitoring in many places, polymer coupon monitoring in some places, and then there are special campaigns with retrofit tools and ROV inspections and whatever. There are a number of different systems. What we have developed is a complementary to these systems. It's not a replacement. And we call it many things. One thing is to call it an optical monitoring system to sort of emphasize the technology, which is to embed optical fibers into the pipe product and embed it along the length where we want to have information, and then we can plug it in and get automatic data from the risers. And there are no external parts on the risers, and there are no electrics at the riser deck, which are important features. The system is made, as you can see on the screen here. We have the fibers illustrated in the pipe, which is going along, depending on whether we are measuring temperature or wire strain. They're located in different places. I'll get back to that. And then we have an interrogator laser interrogator, and we have a data collection system. All you can see from the outside is actually the plug, which is where you take the cap off and plug in the connector after installation of the pipe. The pipe can be wet stored in this condition with the hood on, and then you just plug in with the optical fiber, and then you are hooked onto the network on the rig. The temperature monitoring is based on the standard telecom fibers, and they are helically wound around the length of the pipe all the way. And these fibers, we typically have a couple for redundancy, they give us a temperature measurement for each meter of optical fiber. And since it's wound around the pipe, we end up having a resolution of about 25 centimeters for the pipe supplied, which is a very fine resolution and gives a lot of opportunity to look in detail at the measurements. We can typically pick up data for one data point or one length, a signature of the pipe once a minute. If we look at the different cases, applications, if there is some kind of damage to the outer sheath of the pipe, that will show up in the measurements. And I'll show just an exploded view of a pipe where we have the carcass in the middle, and we have the inner liner, and we have the pressure armoring, tensile armoring, and the outer sheath. And here we can see the red curve that illustrates the temperature profile through the cross section for an intact pipe, where the temperature drops take place over the polymers. And then when you have an opening in the outer sheath, you will have the drop taking place all the way in by the inner liner. So the distance between the red and the blue curve here is the signal, or the change in signal due to the event. Similarly, we have issues of hotspots under bend restrictors or bend stiffeners. Here it's a bend stiffener where we have the insulation by the bending stiffener, by the polymers, which gives increased temperatures of the outer sheet and on the inside of the bend stiffener, which leads to fast degradation of, or can lead to fast degradation of the outer sheet. Similarly, for bend restrictors, we also have some fine insulation here from the bend restrictors, which in some cases can lead to high temperatures. Then we can detect burial or unburial of pipes. If there's a burial of a pipe, there's an increased insulation, so the temperature will be different from other sections of the pipe. And changes in the temperature differences along the pipe are indications of changes to the condition of the pipe at a given point. So hereby we can monitor how the pipe, where the pipe is, also whether it has made its way out through a rock dump by thermal effects or other effects. It'll show up as a change in the temperature. And an important thing which has been mentioned a couple of times is the effects of cold spots, where you can get plugs forming, hydros forming within the pipes. And this information gives the possibility of controlling operations like controlled shutdowns, optimizing the duration of shutdowns without running into problems. Then another point which has been mentioned is all the jewelry, all the components mounted on the pipes, where the bend stiffeners, the distributed buoyancy modules, clamps, and bend restrictors all show up in the measurements because of their insulating effect. And that can be used to keep an eye without having to go underwater. You can keep an eye and check that the components are there and in exactly the same place as last time you looked at it. This is a constructed curve just to illustrate the situation. We have starting from the right, where if we look at the flow, we have the effect of the bend restrictor over in the far, and then we move to the side when we go from the PLEM and towards the FPSO, and there the burial is, the bend restrictor shows up, the burial shows up, and the clamp and the distributed buoyancy modules, and the bend stiffener shows up, and also the cooling slope along the pipe shows up. I'll get back to some of this just in a minute. But the other feature is the strain monitoring, which we have developed and used and supplied, and it is developed both for fatigue monitoring of fatigue issues and for monitoring of wire breakage. I'll focus on the fatigue issues in this presentation, which as the fatigue issue seems to be the most interesting one for the Norwegian applications, which are not the extreme water depth. So here we have the principle is that we integrate the fibers into typically 8 of the tensile wires, and that we mount the fibers in grooves, finely machined grooves in the tensile wires, and then they are glued to the wires, and thereby when you have strain in the wires, you get strain in the fibers. And the principle for this measurement is what's called fiber Bragg gratings, which is gratings imprinted into the fibers themselves, and the effect is the same as for strain gauges, that that we see what is the elongation locally at the location of the sensor. And when you stretch the fiber, you can say the color of the reflection going back to the interrogator changes, and thereby you have an indication, or you have a number for the strain at the location. Typically, these strains are picked up at a frequency of 10 hertz, thereby picking up the motions and loads coming from also from the hang-off. These black rings, they indicate levels or elevations where we have a line of brake gratings going around the pipe in all 8 instrumental wires. And by selecting where we want to have these brake gratings, we can decide where do we want to measure, where do we want to get the information. And it's irrespective of whether it's inside an eye tube or underneath a bend stiffener or whatever. And the data can be used in many ways depending on how you combine them with other information like vessel motions, weather conditions, design statistics, whatever you can come up with. But basically, what you can do as a basic way of doing it is to use the SN curves, applicable SN curves, and use the counts directly from the sensors. And here it's shown. You have the instrumented wires, the instrumented wire number 1 through 8, and then you have counts at different levels of these black rings I showed, and there you can go and pick the highest number as the simplest way of assessing the accumulated fatigue damage for the riser. I'll not spend more time on the fatigue at this point, but I'd like to instead present some qualification of the temperature setup. But basically, as I just said, we have the system with the end fitting, a connector. Sorry, what happened there? The end fitting with a plug-in, and we have the communication cables going to a control room, which can be at a whole different area of the platform. And then we have the data logging, and the data can go anywhere, and it can be presented in any way desired. We have some suggestions, but I'm sure that every operator will have its own ideas, his or her own ideas. So it's a very open thing for custom design, depending on the needs. What we've done during the qualification of the temperature monitoring is to take a standard piece of pipe, insulated pipe, and mount standard end fittings, and then mount a bend restrictor and add insulation to simulate burial, and a buoyancy module, and then to add some inlets where we could control what's happening. And this test setup, it's some 30 odd meters long pipe, and we have the platform here where we have the temperature controlled circulation, so we can get stable condition in the bore, and a controlled difference with ambient water, seawater. And this is just an illustration of the pipe after we just straighten out the data, straighten out the pipe, and you can see the actual print of the different components in a stable condition. This is done with a 38-degree difference between the bore and the ambient sea, and the different items show up clearly in this signature of the pipe. There's something which could look like variations in the measurements here, and they're actually very real variations because they're due to different pitches between the temperature sensor and the insulation layer. So there's a fluctuating temperature at the sensor. What we've done is then to do long-term testing of this, and this is a plot where we have the pipe, as you can see vertically here, the position from the bending stiffener and all the way up to the other end. And we have the time here. At a given time, we have a profile like the graph you just saw. And when we keep doing a long test, we have a very stable indication of the additional insulation, of the buoyancy module, and of the bending stiffener. Then we have a change of the bore temperature, increasing the difference between bore and ambient. It shows up in a change along the length of the pipe. You can see a brief stop in the flow here, and there you see a cooling along the length. So by having this kind of signature on the pipe, we can really follow where the components are and whether they're moved, and we can also make signatures or event detection, so that we have changes over time at a given location, and we have changes over time of the neighboring locations, and thereby events show up. We've made some advanced algorithms that make these sort of what picks up, what our eye picks up. Here's something changing. We can pick that up with quite high accuracy in an automatic process, so we don't have to look at all the uninteresting data. We pick out the interesting ones where there is an event. This is illustrated here by an event where we simulate ingress to the annulus, and that was as you can see, a differential temperature of 34 degrees C, and we had a flow of 0.5 liters per minute, and we ended up putting 15 liters in, and you can see how the effect is spreading along the length of the pipe and over time, and once we stop the ingress, you can see how the cooling takes place, and these start and stop times will show up as events in the analysis. There's a blue spot, as you may have noticed here, and that's called a bottle of Coke size flow. That's simply from disconnecting of the injection line from the deck there of the test setup, and about 0.3 liters went into the pipe, and it showed up directly. By having this system, we've covered quite a few of the most common problem areas or damage mechanisms of the flexible risers. This is from a state-of-the-art report on flexible pipe integrity by MCS, published in May 2010, and in that overview, top score is external sheet damage flooding, and which is well covered by the temperature sensing. There's ancillary device failure, where there are indications whether things have moved or parted from the flexible. There are changes to the temperature effects. What temperatures have the different layers actually seen during operation? There's the wax blockage, and using the fatigue system, the strain system, we cover the armor wire fatigue also. So in short, just the optical monitoring system methodology. It shows system components easily recognizable, clear thermal prints of events. We have real-time monitoring, and we can see the long-term changes. We can see what's happening over time. And with the strange sensing, we have the accumulated fatigue damage, and also an important calibration of design models. And we also use the strain sensing technique extensively in our qualification testing. So my conclusion here, to summarize, is that the option exists. It's a final product. It has been supplied on a number of risers this year, and being supplied on a number of risers this year, and I've been permitted to say that it's for Statoil as the customer who decided to go all in for this, and use the opportunity to get more knowledge. There's no negative effect on the riser design from this. There are no external parts. It complements the other techniques. It's not the answer to all your dreams. In our view and our estimations, the savings in the long run and the advantages far outweigh the capex costs. I know that focus is often on the capex cost until we get first oil, and then suddenly it changes. We offer it as an option in bids. Of course, there are limitations to where it can be used. There may be restrictions on some of the solutions regarding access to end fittings or extreme conditions for the pipes or other issues. And so it's something that has to be assessed in any case. And finally, I'll say that it's up to the operators to choose the solution. It's there, but it can only be used for new pipes. It is not a retrofit solution. Thank you for your attention.
Thank you, Carsten. Very interesting. We have time for some questions.
My name is Stig Opland from Statoil. How many years can this system last? Or how long have you tested it in duration?
In duration, what do you mean?
Have you tested it in a year or 10 years? Or how long period of time will this system function?
The development of this has taken 8-10 years. So it has taken a long time from the first prototypes and until we picked up speed and done this. But it has been used for the qualification testing. These accelerated testings in test rigs. When it comes to the fatigue testing. Excuse me, was that an answer to a question? Okay, what could please clarify that?
Okay, once more. Can we expect this system to last 5 or 10 years or 20 years in operation?
We would expect it to last for the duration of the riser. That's the expectation. And it's clear that there are no moving parts and there are no parts that will burn off, so to speak.
Any more questions?
Paul from Kongsberg. Could you indicate approximately the capex cost comparison with the total cost in percentage?
Well, yeah, roughly, we'll say in the order of maybe 10-15% of the riser cost. It depends very much on what system we're talking about, what riser system we're talking about, and all that. But it'll pay for itself if you save 2 ROV inspections during the lifetime of the riser.